Hello everyone, this is an IGCSE lesson on total internal reflection. What is total internal reflection? Well, it helps if you've been to the reflection lessons that we've been doing. Last week we were talking about what happens when light specifically shines through different materials. So remember we did that activity, we put a tablespoon into some water and we looked at how light shines differently if it's just going through air. But if it's coming through water, then quite often it bends, right? Like we looked at like sort of things like this. You recognise this? So this is a beam of light, I don't know why, coming from water into air. And we looked at how if you imagine that arrow is like a big wave of light. You remember this? Imagine that whole pen is the ray of light. Then this side of the pen, this side of the light wave, hits the air first, and it's easier for light to travel through air, so it speeds up. But this bit of the pen is still in the water, so it's still going slowly. So what happens is that side speeds up and the whole thing bends around, right? Now what we didn't look at, but what you might be able to work out, is that if you change the angle of this light coming out of the water, then this angle up here changes as well. You ready? I tried to show some steps. Let's see how well this came out on the printer. So, can you see that I've made this angle? This is the angle of incidence, yes? This is the incident ray, the one coming out. This is the normal. So the angle of incidence here is a little bit bigger. And can you see that this ray of light is now bent a bit more towards the surface of the water? Yeah? And then this one, we've made that angle of incidence even bigger, and that ray of light is coming down even more towards it. Yeah, do you see what I did? The preparation. What happens eventually is this. We've made this angle so big that this ray of light is just sort of grazing the top of the water. Like, basically what's happened is the angle of refraction, this angle here, is 90 degrees, right? We call this this is a very special situation. This angle here, the angle of incidence that makes the angle of refraction 90 degrees, is called the critical angle. It's the critical angle. Any bigger than that, and what happens? Well, I mean, spoiler, total internal reflection happens, because that's what like this whole lesson is about. This happens. So eventually, if you make the angle of incidence, hope you're okay with this language here, if you make the angle of incidence bigger and bigger and bigger and bigger, eventually the ray of light will be like flat against the, say, swimming pool or whatever. And so that is the critical angle here. And then anything over the critical angle, total internal reflection. Hello, Luke. Let's do an activity to observe total internal reflection. Oh my goodness, so much of my week has been spent experimenting with activities to show total internal reflection, and some of them have failed massively, but I think this one's all right. Just get a tiny piece of paper and like, I don't know, about a postage stamp size, and draw a tiny little stick person on it while I blow my nose off screen. One good thing about being ill last week is that I had to edit my videos, and I noticed how disgusting it is when I blow my nose in the room, as you know. So that's not going to happen anymore. I was like, if I'm finding this gross, they must be finding it utterly... Anyway, this piece of paper is probably a bit big. What we're going to do is we're going to stick our little stick person to the bottom of the inside of our glass, and then see if we can see it. I think I've done a large postage stamp. I'm going to cut that in half, actually. Small postage stamp. Do people even use stamps anymore? Maybe it's only me. About the size of a penny, and then I'm just going to draw a little person on. There we go. Little tiny smile. And then, yeah, get a piece of sellotape and stick that little stick person to the bottom of the outside of the glass. See where I'm doing it? Yeah, bottom of the outside of the glass, isn't it? And we'll see, I mean, if you're ahead of me, how are you going to see an example of total internal reflection by doing this? I didn't find this one on the internet. I made this one up. Here we go. With quite a lot of help from the internet. Right. So, what are we looking for? We're looking for total internal reflection. So light is shining from this little person and through the glass of water and out, right, into the atmosphere. We know this because if you look into the glass of water, you can see the little person. So light rays must be travelling from the person and into my eye somehow. In fact, there's quite a few cool different angles. There's a kind of magnifying effect going on here. But how are we going to see total internal reflection? If this light shining from this person is going to be totally internally reflected, where do we need to put our eye? We need to put it on the other side of the person, right? And we need to be looking up. Oh, it's happening! Because we need light to be shining from the person, hitting the surface of the water, and then travelling back into the glass again. I will show you. If we go below, like this... Oh, there you go, look at that! So we're seeing that image because light is bouncing from that person, hitting the surface of the water, and then going into the camera. Isn't that great? So total internal reflection happens when the first material is denser. Let's come back to that. This is the critical angle here. All right, if you keep bending, then total internal reflection happens. I think that's okay. I think what's a bit confusing is this idea that total internal reflection only happens when light is coming from something that's denser into something that is less dense. So it happens when light comes from water sort of into air, or not, because it gets reflected. But it wouldn't happen if light was going from air into water. There is a brilliant interactive website, which I will link you to, which shows this absolutely beautifully. Here we are, look. So I will link you to this. This is the physics classroom, who I adore. They allow you there's this protractor that you can put on or take off, right? But I've put it on because it's handy, so that we can see our angles. And this is just a laser beam, which goes all the way around, and you just move it around, and then you click go, and it shows you where the laser would go. Isn't that brilliant? And you can change the top substance and the bottom substance. You can make it a vacuum, like no particles, air or water or oil. So at the moment, I've done that. The top one is air. You might be thinking maybe it'll just bounce off the water and into the air if I make it a certain angle. But that will just never happen. Look, it's still being refracted into the water, right? It will never happen because this is a less dense medium, a less dense material, air, and the light is going into a more dense material, and that's not how total internal reflection happens. So you can see, even if I make the angle really, really small, we're not going to get any light. The light is not going to ever completely bounce off the surface of the water. And obviously, if I make the angle too small, then what happens last week happens, and it just sort of pretty much goes straight in. If I make it really big the other way, then will it bounce off? Well, some of it will. We can talk about that at the end for those of you that want to know. But no, it's always going to refract, and it's just because of the way it bends. When light goes into something that's more dense, it bends towards the normal. And I'm not going to go into it too much. You don't need to know, but I just think it's easier if you've seen it yourself. Whereas we can make light come from the water towards the air, and then we do get total internal reflection happening, right? Because the water is denser than the air. Right, I have found some examples. One of these little pictures is not an example of total internal reflection. Which one do you think? And can you explain your answer? Don't just go A or B. Explain your answer, please. You have got A, which is a kind of quite complicated looking diagram, but you've got this thing here where a ray of light is travelling through a lens, hitting a prism, bouncing off it at 90 degrees, hitting the other side of the prism, bouncing off it again at 90 degrees, and then coming out of the prism. That's A. B is like a red spooky tube with a red zigzag bouncing around inside the tube. C is an angle of incidence, a ray of light coming from something called N2 into something called N1, and the angle of refraction is exactly 90 degrees. D is a fish with a reflection of a fish above it, and E is a ray of light travelling, hitting a boundary, and then being reflected back in. And it in Spanish underneath it says reflexio total. And I've put, if you're done, what do you think A and B are? What do you think A and B actually are if you're finished? I've got a brilliant example of A right behind you, but what is A? A is an example of total internal reflection. Well done, I think everyone got that. As light is travelling into this prism, this big bit of glass, but it's not travelling out or through the glass, right? It's kind of bouncing off at 90 degrees and then it's bouncing off again. So that is total internal reflection. I'll show you what that is in a sec. B is indeed total internal reflection. This is a ray of light, kind of like a laser, which is being totally internally reflected along a tube. It's not coming out of the tube. There's no reason why you would know that. We will learn about this. B, well, D, well done. I saw that pretty much everyone was getting that, because that's exactly what we just did with our little person on the side of our glass. That's the fish being the light being totally internally reflected into the camera. And yeah, reflexio total is total internal reflection, presumably, but in Spanish. So this is the dotted line, this is the normal here. So I guess the outside is probably air and the inside is probably water. And yeah, we've got total internal reflection happening. Please note, by the way, remember when we did our reflection lesson, this angle here, this is the angle of incidence between the normal and the incident ray. And this is the angle of reflection, right, between the normal and the reflected ray. So those angles are the same because the reflection is happening. Yeah, so it was C. Why is C not total internal reflection? Well, this angle here is the angle where the light just starts to travel along the boundary. So it's not quite being reflected, right? But it's just about to be. So this angle here, this angle of incidence, must be the critical angle. So if this angle gets even a tiny bit bigger, then this ray of light is going to be totally reflected. Okay, is that all right? Whatever this boundary is here. But at the moment it's not being totally internally reflected. The angle of refraction is 90 degrees. So this must be the critical angle. That's the definition of critical angle, is whatever angle makes the angle of refraction 90 degrees. Let's look at some examples. Cat's eyes on the road use total internal reflection, with great thanks to the person who stood in the middle of a road to get this photo. Do not try this at home. Yeah, lovely little simple diagram of how cat's eyes work here. Look, this person's got a laser, lucky them, or a ray box, and they're shining it into a triangular prism. And this is total internal reflection, see? So this ray of light is not being refracted at an angle through the prism. It's being refracted at just such an angle that it's bouncing off. It's being totally internally reflected at this boundary here, and then it's hitting that side of the prism and it's being totally internally reflected again until it comes out. So that's how a cat's eye works. Good, isn't it? It's just basically a tiny bit of sort of glass stuff in the road, and the headlights of the car just get totally internally reflected twice and beam back at the car. Nice. And the other thing, what I've got behind me, binoculars. But if you didn't get that A was binoculars, I had no idea that my binoculars were using total internal reflection. I'm quite ashamed that I had never thought about this before. So I have got these brilliant binoculars, and I researched them very carefully in the way I research everything. I went into a charity shop and they were there, so I bought them. And I'd never noticed that, yeah, on the box it's even showing off about the prisms that it has in it. Look. High index back 4 prisms. Still don't know what they are, but I'm delighted. Yeah, I'd never thought about it actually. Like, if you look at my binoculars, then obviously the lens where the light goes in and the lens that I look through, they're not lined up. That wouldn't work, would it? Obviously something must be happening here in this bend to make the light move this way, and it is. It's total. There's a prism in there. It's called a poroprism. I have learned something. They are massive, Alice. They're so cool. There's a couple of them in there. Doosh, 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 doosh. But yes, you can see it's very, very similar to the cat's eye. And finally, what is this tube? This tube is incredibly important. We probably wouldn't be able to do this lesson without these little tubes. This is called, you've heard of fibre optics? This is an optic fibre, or fibre optics. And this is what it looks like inside. So the lit up bit is this white bit that you can see here, where a laser beam is being shone in at just the right angle that the laser light is being totally internally reflected instead of coming out. Little reminder from last week, don't panic everyone, don't panic. You remember what the refractive index of a material is? The refractive index is how much a material slows light down, and you can just call it N. So the refractive index of a material is the speed of light in a vacuum, like as fast as light can get, divided by the speed of light of the material. So if the speed of light of the material is, if that number's really, really small, if the light travels really slowly, then the thing has got a high refractive index. Okay, so coming back to this little diagram here, right. So what a fibre optic tube is. So these things carry the internet, right? They carry light signals. There will be fibre optics in your house right now. The light is still travelling at like 2/3 the speed of light, just through these tiny, they're like a tenth of a human hair. See them in little bundles, right? And yeah, the light's just zipping along them. Anyway, let's talk about refractive index. Here we go. So the outside of the tube, the optic fibre, has got a lower refractive index. It allows light to travel faster through it. And the middle of the tube has got a high refractive index. Light travels more slowly through it. Okay, I'm a bit worried I'm going to scare some of you off here, but I thought this question was worth asking. Why? Because they might ask you this in the exam. Why does the outside have to have a lower refractive index? So you've got this tube thing. It's like a tube of one material, and it's lined with the tube of another material, okay? And the light bounces around inside it. So the middle bit is made of something with a high refractive index. Light travels quite slowly through the middle bit. And the outside, what it's coated in, is made of something with a low refractive index. Light travels faster through it. Why would you make a fibre like that? No, I was getting very excited by the comment which said, because it's like water coming out, because it's like light coming out of water and into air. Yes, you remember? Total internal reflection only happens when the first material is denser. Yeah, it's exactly like that. It's like having a tube of water, isn't it, with air on the outside. I mean, obviously that wouldn't happen, but it's got to be denser in the middle and less dense on the outside, because that's when total internal reflection happens. Remember, if it was like air with water on the outside, then it wouldn't totally internally reflect. It would refract and like escape. Yes, brilliant. Obviously, like for an exam, you would just put, because total internal reflection only happens when the first material is denser, so the inside of the tube has to be denser than the outside for total internal reflection to occur. Right. Little trigonometry interval now, so you could just like get some popcorn, put your feet up. We need to talk a little bit about trig, because we need to talk about sine again, and I thought, I need to tell you what sine is. So yeah, I knew I'd taught you trigonometry before, and I had. Here's a little screenshot of me at Christmas during the Forces and Motion lesson 14 lesson. So if you came to that one, you do know about this. Look, I knew I'd written sine on the board at some point before. So very quick trigonometry recap. Exactly, Natalie, yeah, just grab the popcorn. If you've got an angle and you want to know what it is, here's what you do. Let's call the angle theta, okay, just this little symbol. What do? You want to know this angle? Well, you've got a calculator, hopefully, with sine on it. Sine of this angle equals the side opposite the angle, whatever that may be, divided by the long side of the triangle, which is the hypotenuse, okay? Some of you will never have heard of this, some of you will be very comfortable with this. The sine of theta, and we're not going to talk intimately about what sine is, it's on your calculator, and it means the opposite of the angle divided by the hypotenuse, okay? So if we had something that looked like this, the opposite side is 1 and the long side is 2, you'd say, all right, the sine of theta equals 1 divided by 2, the opposite divided by the hypotenuse, 1 divided by 2. And you would get a number, right? So now the sine of theta equals 0.5. But you need theta, not sine theta. So what you need to do is like unsign each side. And unsigning something means sine minus 1. I'm going quickly because a lot of you know, if you don't know, you are going to have to look up trigonometry. But I thought rather than just keep banging on about sine and you have no idea what it means. So to find theta, you unsign each side, which means sine minus 1. So if you do sine minus 1 of sine theta, you just end up with theta. And if you do sine minus 1 of 0.5, you end up with sine minus 1 of 0.5. And then you just put that into your calculator, right? Let's do it. On my calculator, I do shift, and then I find the sine button, because if I press shift first, then it does sine minus 1 for me. And I put in 0.5, And then we press N equals, and we get, oh, look at that, 30 degrees. A beautiful answer. It's like I prepared it. Right, so this is just a very quick recap to sort of get you warmed up for what sine means, because we need to talk about sine. We talked about sine last week a little bit, right? We talked about how you get the refractive index of a material, how much something slows something down is like the sine of the incident angle divided by the sine of the angle of refraction. So last week we did this example, like, all right, say light goes into a glass block at 50 degrees, and then it gets refracted by an angle of 31 degrees. What would be the refractive index of that glass? How much would the glass be slowing the light down? So we said, okay, well, we'll just do sine 50, because that's sine the angle of incidence, divided by sine 31, because that's sine the angle of refraction. So we didn't really worry too much about what sine was. But we need to look at sine again, because there's another equation we get to use. Yay! For the critical angle. This angle has a special name, okay? It's now the critical angle. That specific number for I is the critical angle, because you can see it's making the angle of refraction 90 degrees. So instead of saying I, we're going to say C, all right? It just means C is the angle of incidence, but when it's the critical angle that makes the angle of refraction 90 degrees. Right. Whew! Here's your equation. The sine of C equals 1 divided by n. That's better than last week, isn't it? There's only one sine. Phew! So the sine of the critical angle equals 1 divided by, well, I'll show you what these things are. C is the critical angle. N is the refractive index of whatever material the light is travelling from. So whatever this grey stuff is, this would be N at the moment, its refractive index. And 1, it just happens to be the refractive index of air. So that's why this equation is a bit simpler, because this equation works for anything coming out of anything into air. If the light ray is coming into air, you can just put a 1 up there. I'm making it sound quite complicated. I'm using a lot of words. You can just plug stuff into this equation if you like. It's nice for you to know where it came from. Okay, so you might get a question like this. Boop. The refractive index of glass is 1.5. Calculate the critical angle for light passing from glass to air. The refractive index of glass is 1.5. Calculate the critical angle for light travelling from glass into air. Okay, so we're looking for the C. So what do? Well, we've got N, it's 1.5. That's the refractive index of glass. So we do sine C equals 1 divided by 1.5. And I get the answer, sine C equals 0.6667. So then I've got to do my sine minus 1 on both sides. Is that okay? I need C on its own, so I've got to do sine minus 1 on this side, because sine minus 1 of sine C is just C. And then I've got to do sine minus 1, 0.6667 as well, which is 42 degrees. This is the kind of time when I really wish I was in the room, so I could look at your faces and see if you're going, yeah, easy, or but let's show you that on my calculator. Okay, we're looking for sine C equals 1.5. So 1 divided by 1.5. So I just do 1 divided by 1.5 in my calculator, first of all. That's the first thing that I do to get that answer. Is that okay? I've got sine C first of all, so I've just done 1 divided by the refractive index of glass, 1 divided by 1.5 to get this answer. That's sine C, but I need C on its own, so I've got to kind of unsine it, which means doing sine minus 1. I'm going to leave that answer in my calculator because it's nice and accurate, right? It's got loads and loads of decimal places. Sorry, Tom, stick with it. So I need to unsign that. So I'm going to do shift sine minus 1. And then I'm just going to put answer, because that will tell the calculator this answer here is what I want to do sine minus 1 of. And then I'm going to press enter. And I get 41.8. Call it 42. Here's a couple of questions for you. If you haven't got a calculator with sine on it, you just do number 3. But here you go. You've got the refractive index of diamond is 2.4. So that would be N. The refractive index of diamond is 2.4. Calculate the critical angle for light passing from diamond to air. And number 2, calculate the critical angle for light passing from ruby to air. The refractive index of ruby is 1.8. Number 3, this is a weird one. Jewels seem to sparkle more. The more light shining on them is internally reflected. I did not know this. What do you think would sparkle more, a jewel with a higher or a lower critical angle? And question 4, because some people love the maths and we don't do as much maths as we really should, to be honest. We don't do as much maths as we do if you were in the classroom with me, because it is quite hard to teach like this. But question 4 is light travels from water to air as shown. So it's going from water at an angle of 25 degrees out into air where the angle of refraction is 18.5 degrees. Can you calculate the critical angle of water given that information? So we're looking for the critical angle if light is going from diamond to air. So we need sine C, okay? So we're going to do 1 divided by the refractive index of diamond, which is 2.4. So sine C equals 1 divided by 2.4, which is 0.4167. But that's only the sine of C. We need to find actually C. So we need to unsign 0.1467. And if we do that, we get the answer 25 degrees. Let's go through question 2 then, and then the people who aren't understanding it, at least you get to see a couple more examples, and then I can set you some for homework. Question 2, calculate the critical angle, so C, for light passing from ruby to air. The refractive index of ruby is 1.8, so we've got sine C equals 1 divided by 1.8, and that gives us 0.555555556. But that's only sine C, so we need to unsign both sides to get C. So C equals sine minus 1, 0.55555, which is 33.7 degrees. Well done if you got that. Alice, I was impressed to see anyone getting the answer to question 3. I have no interest in jewellery at all. It's so refreshing, isn't it, to just have something in life that you just don't care about, and I just don't care about jewellery. But apparently how you cut a diamond is really, really important, because the amount of times that light gets totally internally reflected in a diamond, or whatever jewel it is what makes it so sparkly. Which makes sense, really. Like, the diamond's got to send light into your eyes to be all sparkly, sparkly. So yeah, it's the lower the critical angle. So if it's a small critical angle, that means that there's more angles where total internal reflection happens, if you see what I mean. The critical angle for diamond is 25 degrees, which means that 26 degrees, 27, 28, 29, 30, all those different angles, light is all being totally internally reflected. Whereas the critical angle for ruby is like 34, which means that 26, 27, 28, 29, 30 degrees, all those ones, the light is not being totally internally reflected. So a diamond is more sparkly than a ruby. Let's do question 4, because this is a really good one for putting your knowledge all together. You've got an angle of incidence for water, light coming out of water, and you've got an angle of refraction for air, light coming out into air, but that's not the critical angle, is it? Because the angle of refraction isn't 90 degrees. So you've got I and you've got R, but you want the critical angle of water. So what you needed to do was work out sine I divided by sine R to get N, and then when you knew the refractive index of water, then you could plug that into this equation and finally get C. So let's do that. So N equals sine I divided by sine R, which equals the sine of 25 divided by the sine of 18.5, which equals about 1.3, which is the refractive index of water, okay? That's N. So we've got the refractive index of water now. So the answer is actually 1.33190. So there we go. I'm just going to put that n into this equation and say sine E equals 1 divided by n. But I'm not using this smart little rounded up number. I'm using the number that's on my calculator because it'll make the answer more exact, okay? I've got sine C equals 1 divided by n. And I know that n is this, well, it's actually this number here. I've just done sine 25 divided by sine 18.5, okay, from the last question. So this is the refractive index of water. So I'm going to do 1 divided by that to get sine C. So 1 divided by the answer equals... All right, good. So that's sine C. But now I need to unsign it. I need to do sine minus 1 of that. So on my calculator, do shift and then sine to get sine minus 1 of that answer. Phew, close my bracket, just for neatness. And equals... there we go. Splendid. Right, that's about 49 degrees. Phew, that is pretty much the end of the lesson. I just thought the whole thing of total internal reflection happens when the first material is denser. Like, why is that? So I thought you might be thinking, hang on, why when I look into a beautiful pool of water and I see the clouds and the sky perfectly reflected in the water, why is that not total internal reflection? It feels like it should be, right? If light is travelling from the sky, hitting the water, and then bouncing back into my eye, that should be total internal reflection. But you're telling me that it's not, because you're saying the first material has to be denser, and obviously air is not as optically dense as water. So air, and then hitting water, and then back again. You're telling me that's not total internal reflection. It doesn't make any sense. So I thought I would just, for those of you who were getting a bit cross about that, try and explain again why. So this is not total internal reflection. There's a few things that I missed out of this little awesome demonstration interactive thing. So this is air, this is water. Let's move the laser over here again and press go. I told you that if light travels from air into water, then it just gets refracted. You see this button over here? I clicked hide, but I could click show partial reflection, so I will do now. And let's press go again. Gasp! Look at that. So we have slightly simplified the story for the sake of your exam. Actually, when light shines onto things, generally some of it is refracted and some of it is reflected. And what's beautiful about this interactive is that the brighter the light, the brighter, the bigger, the thicker the line, the more light goes that way. Say the sun was like right overhead pretty much, then most of the light would travel into the water and be refracted. But you can see a little bit of it would bounce off. But if I put the laser all the way over here and click go again, what's going to happen? Oh, look, the vast majority of the light actually is bouncing off the water. Because obviously you do see things reflected in water, but some of it is still getting refracted. And you can't move this laser anywhere where all of the light bounces off and none of it is refracted, okay? Whereas if we come down here, can we move this laser somewhere where, yeah, there you go, yeah. So none of it is getting out of the water now. That is total internal reflection. Phew, okay, right. So it's like, yeah, I don't think that's going to come up in your exam, but it sort of feels like quite a big deal, right? That when you're seeing something reflected off a pond, some of the light is going into the pond, because otherwise it would be weird for the creatures. It would be like total darkness in the pond, even though it's a lovely sunny day outside. But total internal reflection means it's all reflected. Right. Fish must be so confused. Exactly. Perfect way to end the lesson.